Okay, so new section for today, starting to talk about something called a gradient. And I just want to give an algebraic sort of segue into it. First, a quick reminder, here's what our Jacobian matrix looks like in a certain special case. Remember, in general, a Jacobian's a matrix, and it's a matrix that represents a linear transformation. Well, if your function has only one output variable, right? So this is now a linear transformation. The derivative is a linear transformation from Rn to R1, not Rn. And think about the structure of the Jacobian matrix. You get one row for each of the output variables. So if you only have one output variable, you get one row. Right? So this is a sort of an odd little case for real valued functions. The Jacobian has a single row. Okay, fine. So what does the Jacobian do? Well, the Jacobian, this single row, that's what allows us to compute directional derivatives. Right? We compute directional derivatives with the derivative transformation, except in practice, day in and day out, it's a lot easier to work with matrices, and so the Jacobian matrix is that matrix. Okay, so what we have here is just this is what the calculation looks like for, and again I emphasize, this is in the case of real valued functions. Okay, so looking at this formula then, there's a different point of view you can take, and that is to look at how this calculation actually goes down. You look at this matrix times that vector, and well, of course, you do a matrix vector product. And how does a matrix vector product work? Well, let's see here. It's different points of view, but it's this dot that, right? So it's that times that plus that times that plus dot plus these times those, and then finally that times that. It's just a dot product, right? Well, how about I just write it out like that, right? So instead of saying directional derivative is a matrix vector product, how about I write it as directional derivative is literally a dot product of two vectors. Okay. So that's the idea. Now, you might look at this and think, this buys us nothing, right? It's the thing that makes this allowable is also the thing that makes it seemingly pointless. It's the same algebra, right? It's the same, this times that plus this times that plus this times that. So why bother? And the reason we bother is because looking at the way we've got this, again, all the same arithmetic sort of written, as a matrix product, where's our connection to geometry? What do we understand geometrically about matrix vector products? And it's a little tenuous. Matrices represent linear transformations. Linear transformations we can kind of think of geometrically in some cases. On the other hand, a dot product, we have strong connections to geometry there, right? So what we're really doing here is taking a new point of view on, it's the same calculation, but it's a new point of view on it with an eye toward geometry, and that's going to help us understand some neat geometric facts. Specifically, it's going to help us understand this thing, this new column vector that we've just written down. I mean, it's the Jacobian matrix, but it's the Jacobian matrix turned sideways, right? Turn your head like that kind of a deal. Okay. All right. Turns out this is geometrically natural. Okay, so this is worth having a name and a notation, it's going to turn out. So this vector, this thing, whose dot products give you directional derivatives, this thing, we're going to call it the gradient of the function. And it's that same formula right there. Right? And we're going to use this notation. It's kind of an odd little notation. This is a triangle. Make sure to write the triangle correctly. Every so often a student incorrectly writes this as that. This is not the same. It actually means something different in math. Aside from, it's a delta, right? Sure, it's delta x, delta y, stuff like that. But it also means another different thing that has to do with partial differential equations, and it's not something we're going to do much of in this course. So anyway, make sure the triangle has its arrow, it has its vertex pointing down. That's critical. Okay. All right. So with this new notation for our gradient vector, we can rewrite this equation up here. We can rewrite that equation as that, and this is our theorem. And again, there's not any particularly new knowledge in how we've written this right now, but here we have the opportunity to possibly gain some new knowledge by interpreting this as a dot product. Okay, now before we go on to actually doing that, I want to make a quickie observation about Jacobian matrices. So let me remind you, here's our formula for Jacobian matrices. All right, we observed last time that each element in this matrix is a partial derivative of the function whose derivative transformation you're representing. Okay. But it's organized in a certain way, right? So the way that we observed the organization last time was that the columns are all partial derivatives, right? So that first column is the partial derivatives of f with respect to x1, always x1 in that first column. Right. So we had an algebraic sort of organization of the columns, and then of course, the individual entries in that column. Well, yeah, that's the different coordinates of the function. We've got f1, and then f2, and then f blah blah blah, and finally fm. Okay. Notice, as it turns out, that we can also say something about the rows. In fact, if you just look at that formula for the first row, it's all of the partial derivatives of the component function f1, f1 being as it is a single component of the f function. F1 is real valued, and therefore that is the gradient vector of f1. And there's our formula for the gradient vector. The gradient vector it's all of the different partial derivatives of that real valued function. Okay. All right. Neat fact. Another important thing to make sure to understand about the Jacobian. By the way, a very common mistake students make with Jacobians is to inadvertently transpose it. It's a surprisingly easy thing to do, and because it's going to be organized, and the rows and columns have to do one way or the other with the input and output variables, but getting it backwards, again, common mistake. So please think it through, make sure you can get that right every time. If you transpose the Jacobian matrix and, have rows be columns and columns be rows, it's extremely wrong, and that's a big problem. So, okay, that was just a quick aside. So here is now a question I want to ask that's going to have a lovely answer. Let's think about all possible unit vectors. Let me come up to my picture. Let's look at this picture here. I am sitting at a certain point in R2, let's say. It could be R3, whatever, Rn. There is some function that I'm interested in, some function f. Maybe it's temperature, maybe it's altitude, maybe whatever. And at this point, A, where I am, I want to consider all possible unit vectors representing directions in which I might, start moving from the point A. And the question I want to ask is, of all these possible directions, which one makes F change the fastest? Now, it's not hard to come up with scenarios where you might be interested in this. Maybe F represents mosquito concentration. You want that mosquito concentration to decrease as fast as possible. Right now, an answer you could say is run. Right? Well, sure. Yeah. So it's a given. Of course, I am going to be running as fast as my legs can carry me. But I would like to make sure that I'm not handicapping myself by running the wrong way. I would like to make sure to be running in the exact best direction. So without clocking and knowing my exact speed capabilities, we could still very reasonably ask the question, okay, yeah, run as fast as you can, that's a given, but which direction should you run as fast as you can? Right. So we're going to look at all these unit vectors here, all of these different unit vectors, and we're going to ask which one maximizes the unit directional derivative. Reasonable question. Okay. All right. Okay. Oh, why did I erase that? Let's keep that there. Okay. So let's suppose that I decide to move in a particular unit vector direction, and let's compute what that unit directional derivative is. So there's going to be a corresponding unit directional derivative here. And this is something we can compute. Here's a calculation. Here's how we compute unit directional derivatives. Dot product with the gradient. Formula on the previous page. Now here's that reference to to dot products. Geometrically, what we know about dot products. Dot products of two vectors can be computed as magnitude of the first vector times magnitude of the second vector times the cosine of the angle between them. There's that old formula from chapter 1. Right. Okay. Now keep in mind, this, our premise is that we're looking at a unit vector here. I mean, again, run as fast as you can. That part's clear, right? It's the direction and only the direction we're trying to focus on here. So we're looking only at unit vectors, so that has magnitude 1. So we're just going to cancel that off. And here's the formula then for the unit directional derivative. It's this expression right here. Okay, so of all the different unit vectors, which one makes this expression the biggest? Now let's come back up to our picture. Here's our picture. We're looking at all these different possible unit vectors. One thing to notice, all of these unit vectors, they're all, we're contemplating a scenario where we're at this same point A. It's at that same point A we have, in fact, the gradient vector is the same. The gradient vector doesn't depend on which unit vector you dot it with. The gradient vector depends only on location. In all these scenarios we're considering starting at the same location, right? So this magnitude of the gradient is independent of what we're looking for. Right? It's constant as far as we're concerned. So the question really boils down then to very simply, how do I maximize cosine theta? That's what I want to maximize. If I can make cosine theta as big as possible, then I make this product as big as possible. That makes the unit directional derivative as big as possible. Back up to the picture. How do I make the cosine of that angle as big as possible? And the answer is make that angle 0. Or, 2 pi is the same as 0, of course. Okay. So the answer to the question then of all these different unit vectors, the best one is the one where that angle is 0. Namely, the best one is the one that points in the same direction as the gradient vector itself. Everybody good? So that's a neat conclusion. What this tells us is that the gradient vector always points in the, what I'm going to call the optimal direction. Now, how surprising is that? Reminder, where did our gradient vector come from? Our gradient vector came as a kind of a algebraic rewrite. The motivation for writing down the gradient was completely algebraic. And yet, oddly, it's the answer to a very natural question. Geometric question even, of all the different directions that I can move, which one, achieves a certain task. Okay. Yep.
Does that work both ways? So like for mosquitoes, you're trying to find the least of them?
Yeah, that's right. Okay, so the premise here was that I was trying to maximize the directional derivative. If you want to minimize the directional derivative, and which, by the way, in the mosquito example, we're trying to reduce mosquito concentration, not increase. Yeah, right. So you go the exact opposite direction. Yeah. Very good question. Thank you for that. Yeah. Okay, so what we have then, here's our conclusion. Whoops, with the wrong button. The unit vector pointing in the, the unit vector pointing in the direction of the gradient vector, and don't forget we have an easy way of finding a unit vector pointing in a given direction. That's just divide by the magnitude. So the unit vector in the direction of the gradient is what we call the direction of fastest increase. That's the way to go to make your function increase the fastest. And then, again, if you want to make your function decrease as fast as possible, go the opposite, negative direction. Okay, now an alternative terminology I want you all to be aware of. This is more common, but I think less natural. I've always been uncomfortable with this terminology. Let's consider the special case where we are actually looking at a graph. And again, we won't always be. Arguably, we usually won't be looking at a graph. But if you were looking at a graph, so z is a function of x and y, right? Notice that trying to make the function increase as fast as possible is the same as trying to make z increase as fast as possible, which means I'm trying to make height increase as fast as possible. And thinking about, directions that you might go in the domain, how would you move in the domain, all these different possible choices. And you want to make height increase as fast as possible. The way you would say that is, well, we're looking to have our movement on the graph be as steep as possible. Steepness says how fast is the height increasing as you move in the projection, in the domain there, right? So another alternative terminology, instead of direction of fastest increase, sometimes people say direction of steepest ascent. Again, this is fine. You're probably going to hear this terminology, direction of steepest ascent, probably even more than direction of fastest increase. But it makes sense only from a much more limited set of assumptions. This assumes, right, if you want to say direction of steepest ascent, it assumes you're looking at a graph. If you're not looking at a graph, then steepest is a very unnatural terminology to use. So, anyway, that's my little complaint about that. Okay. All right, next question we're going to ask, and this is just a calculation, but let's suppose that we've back to this scenario, and we've decided, okay, well, I want to make this directional derivative as large as possible. How do I maximize that? And the answer was we're going to go in the direction of the gradient vector. Run as fast as you can, that's a given, but what direction do you run? Direction of the gradient vector. In this premise, given that we're going that way, what is that directional derivative actually equal to? What is that unit directional derivative actually equal to? Now again, I don't want to assume that I know how fast I can run, right? Who knows how fast I can run when I'm being bitten by mosquitoes? I don't know how to measure that, right? I don't want to play that game. But per distance that I run screaming, right? How fast is this function? Again, well, decreasing if I'm going in the opposite way. But so what is that unit directional derivative? Now, this is just a straight calculation, and it's just pluggy-chuggy. So, again, here's our formula for how to compute unit directional derivatives. We just agreed that I'm going to go in the direction of the gradient vector. So this dot product is that dot product. And, oh, hey, look at this. Here I see gradient dot itself. And that gives you magnitude squared. And so altogether, I have magnitude squared divided by magnitude, and that gives you magnitude. And so weirdly, the gradient is the answer to another question, which is, what is these, and again, how do you want to say it? What's the maximum possible rate of change of the function per unit distance? Or, looking at a graph, how steep is that graph in the steepest direction, of course? So I like to summarize this by writing the answers to the two questions that we've just asked as statements about the geometric characteristics of the gradient. Here they are, the two geometric characterizations of the gradient. Direction and length. That's what a vector is, direction and a magnitude. And both of these geometric features of the gradient are natural things. The direction of the gradient is the direction of fastest increase. Natural. The length of the gradient says how steep or how fast is the function changing in that direction. And that's kind of nice. Everybody on board? All right. Okay, so here's another surprisingly natural feature that the gradient vector has to do with level sets. So make sure to remember what a level set is. A level set is where you're setting a function equal to a constant. So looking at this picture here, if we have a function f, right? If you set the function equal to a constant, some constant fixed value c, right? Then the level set is the set of points for which f is equal to c. So everywhere on this surface, we have f is equal to c. So I'm going to write that down here. Everywhere on here, f equals c. That same value c. Okay. All right. So notice a reminder. We already know this, but level sets live in the domain of our function. Again, our function is we've got a real valued function defined on R3 in this picture. Level sets live in the domain. Gradient vectors also live in the domain. Right? If you write down the formula for the gradient, right, the formula is you take the partials with respect to all of the input variables. And so there is one component for each input variable. Therefore, this lives in the space where the inputs come from. This lives in the domain. All right. And it turns out that at a given point, you fix a given point on that level set, the gradient vector has a geometric relationship with the level set, and the geometric relationship is that they are perpendicular. Orthogonal. So again, pretty surprising. I emphasize this is geometrically natural, right? Perpendicularity is a statement about directions. That's an intrinsically geometric idea. All right, so I'd like to persuade you of why this is true. It's not immediately obvious. It's a little bit of an eyebrow raiser. Why should this be? What do gradients have to do with level sets anyway? Right? And the argument here is actually pretty straight. Oh, again, I erased too much. Why am I? The argument's pretty straightforward, though. I just want to erase that, I suppose. Here's the argument. Again, let's remind ourselves that we've got some function here, and we're looking at some fixed constant value c. There, we're looking at the level set corresponding to that value c. And what I'd like to do now is I would like to suppose that I am moving along some curve entirely in that level set. Oh, gosh. I'll use that color. Okay, here we go. So let's suppose that I'm moving along this curve x of t. And I ask what's happening to the function as I move along that curve. And keep in mind that curve is entirely within this level set, and on this level set, f is always c, right? Which is constant. This is that same constant there. So as I move along this blue curve, x of t, f is constant. F is always c everywhere along that entire curve because the entire curve is in the level set. So this is, I think, a pretty believable observation. Yeah. Well, if f is constant, then that means, again, as I am moving along this curve, x of t, if f is constant, that means that the derivative of f is 0. Yeah. Now, let's take a closer look at this curve. This curve here, x of t, at that moment when t is equal to 0, Here, I'll zoom in. At that moment when t is equal to 0, when we're at the point that we're interested in, we are at the point A and moving with velocity equal to, well, some velocity, dx dt, however you want to say it. I'm going to say that the velocity vector, let's give it a name, let's call it v. So this expression here, we're taking the derivative of the values of the function f while I'm at the point A moving with velocity v. This is a directional derivative. Let me use a different color choice here. Yeah, that is, it's the directional derivative. It's the v directional derivative of f at the point A. Oh, that circling is terrible. Let's do that again. Yeah, because that's what x is. X is at the point A moving with velocity v. With that in mind, this is straight up the definition of a directional derivative. Okay, so, all right, this means that the directional derivative is equal to 0. Now, wait a second. What does that mean if the directional derivative is equal to 0, coming down here? The directional derivative is equal to 0. Don't forget we have a formula for how to compute directional derivatives. Directional derivatives are dot products with the gradient. And so what I get then is this dot product is equal to 0. That means that these two vectors are orthogonal. And that's what we were trying to prove, in fact. Right, you see the gradient is, as long as it's not 0, perpendicular to every tangent vector to the surface. And let me go back up to the picture. That velocity vector, notice that velocity vector being a velocity vector of a curve that's entirely in the surface, that is tangent to the surface. So this means that our gradient vector, this thing that we're trying to understand, that gradient vector is always perpendicular to every tangent vector, and therefore it's perpendicular to the surface. Yep.
Just for clarification.
Yeah.
Is the curve within this, on the surface?
It's on. Yeah. So a surface is when I say on the surface or in the surface, in meaning is a subset of, right? Yeah. So what the surface may or may not enclose is not what we're interested in. Yeah. So mathematicians use the word in a different way.
Okay.
Yeah. It's a great question. Thank you for clarifying on that. Yeah. Right. Okay. In fact, keep in mind the surface doesn't necessarily have to enclose anything. Yeah. Right. Okay. So some quick examples, and then we'll move on. We've seen a bunch of things that you can do with gradient vectors. This is a revisiting of an old example from section 4.3. Here's a function. Let's compute the directional derivative at the point A moving with velocity v. Well, this is, you can go straight from the definition, plug and chug, brute force. That's what we did back in 4.3. Or you could use a Jacobian. That's what we would have done yesterday, right? Here, let's use the gradient vector. It's algebraically not that different, but the gradient vector is the vector of partial derivatives. Those are easy partial derivatives to compute. You plug in the point that we're at. That tells you the specific value of the gradient vector at the point we're interested in. And then directional derivative is dot product with the gradient. Namely, it's that. Notice we're dotting with the velocity vector. And there you go. Now, if we had done this with a Jacobian matrix, it would have looked, practically identical. It just the gradient would have been sideways, right? It'd be Jacobian gradient. But other than that, it'd be the same stuff. Okay. All right, next question. Looking back at that same function, in what direction is the function increasing the fastest? Well, this is these should be the questions that you are most hoping show up on a midterm exam because the answer is always, it's highly methodical. It's algorithmic. The direction the function's increasing the fastest, direction of the gradient vector divided by its own magnitude. Bam. Very, very, very formula, very quick. Too, not a lot of tedious calculations. So these are highly desirable questions. Okay, here's a tricky one. Let's look at this real valued function here. That's defined on R3. So just for context, we have here. Colors. Here's R3. This function is real valued, and we're going to look at a certain level set. Oh, let me do this in green. We're going to look at a certain level set of f. The level set that goes through the point 132. That point 132, of course, is going to have a certain output value, and if we pick that output value, look at the corresponding level set for that output value, we're going to get some surface. And I am not exactly sure what that surface looks like because, my gosh, look at the equation. The equation of this surface is e to the xy plus xz squared equals whatever that constant is. I'm going to go ahead and assume that anyone who has a phone is checking to see what that siren means, and if we're in trouble, you'll let me know. Fingers crossed. Okay, so how do I draw this surface? Yikes, right? This is a tough surface to draw. And what the question is asking us is how do we find the equation of the tangent plane? Okay, well, the tangent plane at that point, something like that. How would I find the equation of the tangent plane? Okay. Especially given that I can't draw the picture itself, it's a little hard to figure. Okay. So what we're going to do is we're going to argue as follows. I know that the gradient of this function f, the gradient is perpendicular to the surface. Well, if the gradient is perpendicular to the surface, then the gradient is also perpendicular to the tangent plane. And if it's perpendicular to the tangent plane, then I can use it as my normal vector. And now I've got a normal vector for the plane. I was given a point in the plane here. Let's see here. So I was given this point in the plane. That'll be my x naught. And I now have n and x naught, and I can just write down the equation of the plane. And there's some, here's the algebra here. You got to compute that normal vector, that gradient vector. There's the partial derivatives. We're interested in what's happening at this point. So, of course, you plug in that point, and there's your normal vector. And you can see that normal vector right here in the resulting equation for the plane. Everybody on board? Yeah. Okay. All right. So gradients again, kind of a weird little story. We write them down initially as just an algebraic kind of notational alternative, and then it turns out that they're crazy natural. They always have this wonderful geometric relationship of being perpendicular to level sets. They always point in the direction of fastest increase. Their magnitude is always equal to the unit directional derivative in that optimal direction. They're super useful geometrically. Okay. All right, moving along. I'm going to talk about the chain rule. Here's a picture, as I like to draw it, of how to think about the single variable chain rule. Now, by the way, I am assuming that y'all are computationally proficient with the single variable chain rule. I also assume that you understand what the chain rule means. Right? So this is not, I'm not trying to tell you something you don't already know here. What I'd like to do here is take a different point of view on the single variable chain rule that maybe you have, maybe you haven't seen, and think about it in those terms so that it will generalize nicely to the multivariable context. Again, I'm going to do that a lot in this class. I'm going to segue into multivariable ideas by taking a certain point of view on the corresponding single variable idea. Okay, so chain rule. Chain rule is about derivatives of a composition. this is what a composition looks like. I plug in the output of one function goes into the input of the next function. Okay, so in this scenario, y is f of x, and z is g of y. And we could presume that this point A, it has some image f of A, and that point f of A has some image g compose f of A. And that's just kind of groundwork. Okay, now what would happen if I were to, at this point A, what would have happened if I just took off and started moving? Well, look, these points over here, these are the images of, well, I've got this point that's now moving. X is now changing. Well, that means Y and Z are going to change. So there's going to be a corresponding dy dt, and there's going to be a corresponding dz dt. Okay, and these velocity vectors are all related by derivatives. Now, reminder, here's a point of view on derivatives. The derivative of f is the thing that relates those input velocities and output velocities. So now, different ways to say that. The way I'm going to say it here is that the relationship between those vectors is that you multiply by f prime. Right, f prime is what you multiply by dx dt to get dy dt. I just want to make sure everybody's happy, right? Everybody on board. That's an interpretation we've taken before. Right, now just to be clear, it's f prime, the derivative of f, well, at the point, of course, where we're actually evaluating f. Now, it's not f prime of b. All right, it's f prime of, well, where are you? What are you plugging into f? Well, so f prime of a. Okay, that's the relationship between those velocities. Now, let's look at what's the relationship between these velocities. Well, those are input and output velocities for the g function. Right? And the relationship, again, is that you multiply by the derivative. So this connection, this is multiplication by g prime. Now, again, be careful. It's not g prime of any point you feel like, or g prime of some random, b or whatever. And very importantly, it's also not g prime of a, because a is way over here. G is not being evaluated at A, right? G is being evaluated at that point right there, f of A. So G prime also evaluated at f of A. Okay. All right. So the way you might say, the way you get from dx dt to dy dt is you multiply by one factor, and then from dy dt to dz dt you multiply by this other factor. We know those two factors. All together then, if you want to know how to, what is the relationship between dx dt and dz dt, namely by way of the composition, which, by the way, again, just interpreting as derivatives, that is multiplication by the derivative of that function, evaluated at A, of course. Right? I now have 2 points of view on how to relate dz dt and dx dt. On the one hand, I multiply by that value. On the other hand, I multiply by both of these factors. Therefore, those have to be equal. Right? Multiplication by the derivative of the composition has to be the same as multiplication by, the product of these individual derivatives, evaluated appropriately, of course. And that gives us our single variable chain rule that y'all all remember. This is the Newton notation for the single variable chain rule. Of course, the Leibniz notation, dz dx equals dz dy times dy dx, right? Has its appeal. It has its moments. But I want to use specifically the Newton notation here. How are we doing? Is everybody on board? Okay. All right. So again, it's not that you didn't know this. It's that I wanted to set up this particular point of view so that when let's try to do the same thing in the multivariable context, and I want us to be all set up for this to just, go through nice and smooth. So here's the multivariable version of that same story. We've got a composition of two functions, f, domain and target like that, g, domain and target like this, right? I could imagine that I have a point A, it's going to have an image f of A, which itself will have its image g compose f of A, right? I can call those x, y, and z. I could imagine what happens if x starts moving with a certain velocity, and of course that means all these other points are going to start moving too, with yet to be determined velocities. Right? And okay, so what's the relationship between these velocities, and how does that tell us anything about the relationships between the derivatives of these functions? So I'm going to apply the same strategy. Let's start by looking at these two vectors. Yeah, I'm sorry, let me circle that a little bit differently. I want to give myself some room to write here. How do I take a dx dt and turn that into a dy dt? And the answer is we apply the derivative transformation. Now, back in a Calc 1 context, it's, you multiply by the derivative of the function f. In this multivariable context, it's you apply the derivative transformation of f. But that derivative transformation is the relationship between input velocities and output velocities. Again, per our discussion last time. Okay, so I'm going to say, plug into the derivative transformation df. Okay. All right. Now let's see here. Let's continuing the pattern. Y'all can probably guess how this is going to go down. What's the relationship between dy dt and dz dt? Yeah, it's by way of the derivative of, I guess I should go ahead and do this. By the way, the derivative of the g function, just like this was the derivative of the f function. So, colors, we're going to plug in dy dt into the derivative transformation of g. What about the composition? Well, what's the relationship between those vectors, which, by the way, it has to be the derivative of the composition. So altogether, I'm just plugging in effectively into the derivative transformation of g compose f. And what that means then is altogether, these two processes are the same. Thinking of, colors again. Thinking of dx dt and dz dt being related by a sort of a two-step process, it's got to give me the same answer as thinking of that relationship as being part of a one-step process. And so therefore, the derivative of the composition is just, whatever you get by doing this two-step process. Which, by the way, notice is we're going to first do the derivative transformation of f, and after that we're going to apply the derivative transformation of g. And that's really easy to write down, as it turns out. Here it is. The derivative transformation of the composition says, first plug into the derivative transformation of f, then plug into the derivative transformation of g. And by the way, notice what that means is this sort of successive application of these derivative transformations means that we are, in fact, composing those derivative transformations. So we get really a very elegant little formula here, which is that the derivative of a composition is the composition of the two individual derivatives. How nice is that? Everybody good? This is just algebraically writing down what we argued in that picture. Okay. By the way, don't forget compositions in the matrix shorthand. Compositions are matrix products, and so another way to say this is that the Jacobian of a composition is the product of the individual Jacobians. And you can hopefully now see why I kind of like the Newton notation for talking about the single variable chain rule, because now this looks just like, it's J instead of prime, right? But this, other than that one little cosmetic difference, looks just like the Newton notation for the single variable chain rule. Cool. All right. So this is our big new tool. It's called the chain rule. I'll give you an example. By the way, one thing you're going to notice with chain rule problems is look at that picture. Look how much is going on. Yikes! Right? It's just there's a lot of things to keep track of, right? One thing you got to keep track of is which function is where, which function is first, and which one function is second. Don't forget, it's kind of backwards, right? So in the composition notation, the one that acts first is on the right, but in the sort of diagram notation, the one that acts first is on the left. And so there's this sort of opposite. Be very, very, very careful with that. Again, I've been stung badly on that mistake in the past, and I don't want y'all to get equally stung. Make sure to get it the right order. But also, look at all the different variables. There's a bunch of different x variables. There's a bunch of different y variables, a bunch of different z variables. And it's important to make sure to keep straight which variables live where. Which variables are inputs for which function, right? So what I encourage you to do is don't try to keep this all in your head. You're gonna make mistakes. It's just practically a given, right? So for example, let's look at this question here, and I'd like to start by criticizing my writing of this question. I didn't enumerate as explicitly as I should have which variables go where, but we're going to be looking for this derivative partial of g3 with respect to x1. By g3, I was intending to suggest the third output variable of the g function, and by x1, I meant the first of these two variables. So let me write out a diagram of what we're supposed to be looking at here. We're looking at this composition. We're doing, let's see here. Which function goes first? We are putting in, here, let me color code. This is what goes into f, right? Out of f comes that vector, which you can see here is then a vector that then goes into G, right? So what goes into f, here's what comes out of f, that's what then goes into G. So you can see it has to be like this. That's the f and that's the G. Just from sort of the way the question's written, the context, that's the order of the composition. Is everybody on board with that? And so heads up, right? Make sure to pay attention and think it through as to which way does it go. Okay. That said, let's put these puzzle pieces together. So this is R2 to R3, which then goes to R3. Now, as we just noted, I'll say these variables are G1, G2, G3, and I should have written that in the statement of the question. Apologies. And over here we have variables x1 and x2. And again, I should have written that in the statement of the question. Okay, there's our little, this is our cheat sheet, our legend, right, for the story that's being told here. This is what fits in where and how so. Okay. So I urge you to make sure to do something like this to keep track. Okay. So notice we have this point 1, 2 living over here in the domain of f, where I know what the Jacobian is, and that point 1, 2 goes by way of f to this point 3, 1, 0. And at the point 3, 1, 0, I know what the Jacobian of G is. Right? So, looking at these Jacobians, let's see here, the Jacobian of f is telling me about the Jacobian of f at that point. And let's see, the Jacobian of g, that's the Jacobian of g at that point. Right? Everybody happy? Okay. So, how am I going to find the Jacobian of the composition? Altogether, looking at the composition, looking at that composition, the Jacobian of the composition, well, the composition is G compose F, and so that's going to be, paying attention to the order, let's see, in this composition, the first one to act is F. The first one to act when you're writing matrix multiplication is on the right. So J of F is over here. Right? And then the second one to act is the Jacobian of G. In the way you write it down in matrix multiplication, it's the one on the left that acts second. So here's the formula that we're going to use for computing the Jacobian of the composition. Okay. And notice those matrices are given. There they are. Make sure to write the product down in the right order. Again, if you get these backwards, you're all messed up. In fact, it doesn't even make any sense. Right? If you try to multiply these matrices in the wrong order, it just wouldn't work out. Now here's how it works out in this case. We have the Jacobian of G on the left. We have the Jacobian of F on the right. And notice this is a matrix product that you can do. If you switched the order of these and had them backwards, you wouldn't have the right number. You couldn't do row dot column because they wouldn't be the right number of entries. It would be meaningless garbage. Okay. Enough of that. So, there you go. Jacobian of the composition is that. Okay. Now, let me look back at the statement of the question here. So the first part of the question was, what's the Jacobian of the composition? Second part of the question was, what is the value of, specifically, of the partial of G3 with respect to x1? Okay, partial of G3 with respect to x1. All right, let me clean up a little bit of my mess here. G3 with respect to x1. Okay, let's see here. G3 is the third output variable with respect to x1, so that is then with respect to the first input variable. And this tells you exactly where in the Jacobian matrix you're going to find this thing. Because you're looking at partial with respect to the first input, you're going to be looking in the first column. Right? Make sure to get this straight if you get it backwards. Partials with respect to certain input variables tells you which column you're looking at. And then likewise, which element in that column, or if you prefer, which row are you in, is told you by the output variable. So we're looking at the element in the third row, first column. And that's just a matter of, okay, there it is. Third row, first column. And so, boom. Okay. Okay, so this is my favorite point of view. I'm going to say this one is my favorite point of view on the chain rule because I like the elegance of compositions. I think it's important to be able to think about derivatives as linear transformations. So I would like for this to be your cornerstone, default point of view of thinking about the chain rule. That said, of course, in practice, matrices are how that's how you get stuff done. That's how people do business, right? Matrices are the shorthand with which we have algebraic tools, and of course you use matrices. That said, in some situations, there's a different point of view on the chain rule that is really, really useful. And so I want to talk about that one now. Now here I have written this is the same chain rule that we wrote on the previous page. Let's see here, zoom in a notch. So here we have the Jacobian of the composition, G compose F. And then here we have the Jacobian of G, and here we have the Jacobian of F. So all I've done here is just write out these Jacobians. Each Jacobian is, of course, a matrix chock full of partial derivatives. So, but let's look at this now as, this monstrous equation involving a bunch of individual partials. Okay. And let's think about how this is a matrix product. And let's look individually at some element of this matrix product, and it doesn't really matter which one we're going to look at. I guess I'll look at that one there. Whatever. How do we compute an individual element of a matrix product? Well, row dot column. Right? So that single partial derivative I can think of as being this row, right, the corresponding row of the left matrix, dot this column, corresponding column of the right matrix. And I can write out that dot product explicitly. Like so. That particular partial derivative sitting inside of that Jacobian matrix of the composition. That particular partial derivative, and now you can see the partials of z with respect to the y variables. You can see those right in there. And you can see here I've done the dots with the partials of those y variables with respect to the given x variable. And there's that dot product. Right? So an alternative way to think about the chain rule, instead of thinking about the chain rule as sort of all at once, if you want to focus on an individual partial derivative, this formula tells you how to compute individual partials. And let the record show, isn't that clunkier? It's bigger. It's a lot less compact, it's a lot less elegant, I think, than the Jacobian point of view. But anyway, that's just a cosmetic point. Okay. Nevertheless, this is an important point of view, and I'd like to give you a different way to think about this, rather than thinking of this exclusively as, well, this is what you unavoidably get by thinking about matrix products. Here is a sort of a flow chart of the variables that are involved. You look at this equation here, look at all the variables involved. Well, there's xj, whichever input variable we're taking the partial with respect to. And then here is zi, the output variable that we're taking the partial of. Right? And then notice those variables show up various other places here in that formula. Which, by the way, no surprise. Look at the way the product is written down. Right? This being partial of z1, that row is made up of partials of z1. Being a partial with respect to xn, these partials over here are all with respect to xn. Right? So there's no surprising. Okay. Well, now what else is showing up in here? You can see here there's y1, there's y2, etc., etc. Right, a bunch of different variables, and finally the last one over here, ym. All right, so that's the sort of the looking at the algebra. The algebra suggests this kind of a diagram. The idea of the diagram here is that we have there's a single sort of input in the original domain. Then there's all the variables in the sort of the intermediate domain, and then there's the last. There's just the one output variable that I'm trying to keep track of. Okay, all right. So now with this context, let's think through how to think about this equation. And here's the idea, and I want to zoom in on the picture for a moment. Look at this diagram. What's the relationship between changes in xj and changes in y1? And the relationship there, it's a derivative. Derivatives relate input changes to output changes. So I'm going to say multiplication by partial of y1 with respect to xj. And now, next question, what is the relationship between changes in y1 and changes in zi? Well, it's multiplication by partial of zi with respect to y1. Right, so if you were to say, I'm going to change xj by a little bit, and I'd like to know how much does that change y1, and then furthermore, how much does that change in y1 propagate over to cause a change in zi? Well, you get the product of those two factors. And you can see that product of those two factors right here in this term of that equation that we just wrote down. You can see the partial of y1 with respect to xj right there, and the partial of zi with respect to y1 right there. Yeah? So let me say that a little bit differently then. This term of the chain rule as we saw it from matrix multiplication is referring to how changes propagate through the intermediate variable y1. Right? Changes in xj eventually get to causing changes in zi, but it does it, at least as far as that term is concerned, by moving through the variable y1. So this is what I'm going to call the y1 term of the chain rule. And then likewise, so this term, changes that go through y1. This term, that's just referring to changes that go through y2, etc. Right? And then dot, 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 and then finally that last term refers to changes that propagate through ym. Okay, so there's a nice way to think about it. You can therefore, instead of writing down your whole monster Jacobian and concluding this as a special case, if you just think about how changes propagate, you can say, look, if I'm interested in this, then I write down those variables, and then one at a time, I think about paths, different paths that move through the intermediate variables, and just looking at those paths, you can motivate all of the terms to write down in your chain rule. Everybody okay? Yeah, okay, cool. And in some circumstances, I mean, the reality is that sometimes, often even, what you're interested in is a single partial derivative. You don't need the whole Jacobian matrix. And if what you're interested in is, in fact, a single partial derivative, why write all this down? Right? When you could just think in terms of intermediate variables and just write down just the one formula that you need from this interpretation. Okay. All right. So looking at the previous exercise that we did, again, let's go back to here. So we wanted to compute the partial of G3 with respect to X1. And we multiplied out and computed this whole matrix and then realized that, oh, well, yeah, but what I'm interested in is just that one element. Well, now let's compute that one element just real quick by itself. That's a dot product of those numbers with those numbers. You can see that dot product playing out right here as there's that row of the left matrix. Here's the corresponding column of the right matrix. And the partial derivative coming from that sort of intermediate variables formula worked out with that arithmetic, and we get the same answer. Didn't have to compute all the rest of the matrix. Okay. Everybody good? Okay. Do beware of one thing. I don't know if y'all have seen this issue before, but there is a temptation for students to want to look at this Leibniz formula for the chain rule, the single variable chain rule, and to just do, oh my gosh, look at that. Oh, they cancel, and therefore it does what it's supposed to. Right? And there's a point of view you can take on that, but in order for this to make sense, you've really got to develop some ideas that are not developed in single variable calculus classes. So this is uncomfortable, I'm going to call it. Right? You can kind of get away with it in a single variable context. Okay. But I must point out, you cannot get away with this kind of nonsense in a multivariable context because it's just wrong. I mean, look at this situation here, right? There'd be a temptation to say, "Oh, I don't need these terms. How about I just just cancel those and then check it out? Partial of G3 with respect to x1. What's wrong with that?" Well, what's wrong with this is that's meaningless garbage, right? And you can see we have therefore missed 2 terms out of 3 in the actual correct computation of that partial derivative, right? So be really, really careful with this. Now, what makes this so dangerous here is when you do this cancellation, you're really not canceling the same things at all. This right here, if you want to think about it as being a thing, that thing right there says it's a change in y1. But with an asterisk. That says we want to think about how y1 changes on the assumption that no other variables at all are changing. Right? So this, as part of this partial derivative, says no other y's are allowed to change at all. What does that say? That says, look, x1 is changing. And as a consequence, y1 is going to change, but so are all of the other y variables also. Right? So the point is, these 2 things, they both represent changes in y1, but they represent changes in y1 in very different scenarios. So they are not the same thing. It is tragic. Unavoidable, I guess. But anyway, it's embedded in the literature. But we can't. This notation is just going to be what it's going to be, right? So it will look like these are the same things, but they aren't. So that's why I like to. Anyway, so just make sure not to do that. That is wildly wrong. Okay. All right. Okay, so real quick, confusion of variables. I'm going to go quick through this because this is a pretty straightforward point. I'm going to start with a silly example. Let's suppose that I wanted to compose that function with that function, x squared, and I want to compose it with x cubed. And what's the derivative of that composition? And well, if you play a little too fast and loose with this, there's a temptation to say, look, derivative of composition is the product of the derivatives, and this has derivative that's that, and this has derivative that's that. And so multiply it out and you get 6x cubed. Well, of course, that's wrong. Because I wasn't being careful. I did not evaluate g prime at f. Right, remember, you have to evaluate g prime at f. You don't evaluate g prime at x. So that's wrong. Okay. If you wanted to be more careful, this point of view, what you'd have to do is you'd have to plug in f of x into the formula for g prime, and plugging in f of x into the formula for g prime. Of course, now g prime is 3x squared. 3 times the variable squared, and again, we're already confused. But notice that means we're doing that to f of x, which is x squared, and now count the x's, and everything adds up just fine. You have x to the 4th times x, and that gives you the correct x to the 5th. Okay, so that's, I don't know, that's a way that you can do this, but I don't like this either because of what I'm going to call a confusion of variables. So let me gripe now as to what's wrong with this. Again, let's make ourselves a little legend or roadmap or whatever you want to call it. What plugs into what, and what variables are ins and outs of what functions. And here it is. F goes into G. Let's see here. The G is written as G. Where did I put it? is written as a function of x, but f is written as a function of x too. And so check this out. X is being used to represent two different things. X is being used to represent the input variable to f and the output variable from f. Well, that's insane. You can't do that. These are different things. You got to give them different names, right? So, looking at this diagram, the way that I would move from this is say, look, if we're going to choose to say that x is the input variable for f, then I'm going to have to give the output variable a different name. Maybe I'll say the output from f is y. And if I am reasonably choosing y to be the output variable name for f, then that had better be what I put in to g. So I need to rewrite the function g. I've got to take what was given here, that I was given that g of x is equal to x cubed, and I've got to say, nuh-uh, not anymore. That doesn't make any sense. X is way over here. So I need to rewrite g, same function. I just need to rewrite it in terms of a variable that I can choose that won't give me this confusion of variables. Right? So that's the big lesson. Just rewrite one of the functions in terms of a different dummy variable, and then everything goes through smooth as glass. So here's how this would go down, avoiding that confusion of variables. Yeah, we're given these two functions, f of x and g of x. Whoa, hey, no, you can't do that. You can't just have g be a function of x. X is the input variable for f. So let's rewrite, let's say, fooey on that. G is now a function of y. Same function. It's still the cubing function. I'm just writing it in terms of a different dummy variable. And now there's no danger of confusion of variables. I don't have to consciously remember don't forget to plug in the function. The variables keep track of everything for us now. Right? So specifically, I can be as sloppy as I want in writing down the chain rule. Composition prime is g prime times f prime. 3y squared times 2x. And notice the fact that this is written down as y tells me that what I have to put in for y, what I have to put in for y is x squared. So don't confuse your variables is the punchline here. If you don't confuse your variables, then life is good. And so that's again, that's in the single variable context. And just very quickly, I'm just going to point out, it's the same deal with multivariable. Y'all can see this coming a mile away, I'm sure. Here's a function f, written in terms of x and y. Here's a function g, written in terms of x and y. If you want to compose them, well, the very moment that you say that you're going to compose them, then you've got to recognize that you've got a confusion of variables problem. If f takes x and y as its inputs, I've got to give different names to the outputs. Maybe I call them u and v. Well, whatever I call the outputs from f, that's got to be the name that I give to the inputs to g. So I've got to rewrite g now in terms of u and v. Here we go. Rewrite g in terms of u and v. Same exact function. Right? And if you do that, there's no confusion of variables when you write down your product of Jacobians. You don't have to remember, don't forget to plug in the thing into the thing. No, it's just the variables keep track of it for you. There you go. And you can see here, right here, by the way, what do you plug in to where? Because g is a function of u and v, that means u and v are the outputs from f. That means u is that thing. You can see it right there in your formula for f. And then V is that thing, and that tells you what to plug in there. Okay. All right, we have 8 seconds left. I don't think we're going to make it. So we'll draw the line right here. Sadly, we did not finish chain rule today. So be it. And see y'all later. Have a good one. I don't have any homework to return, of course, because there was nothing due yesterday. But don't forget to turn in today's homework. And if you came in after I checked attendance, make sure I get you marked off.